last lecture, cover everything I wanted to do. Of course, people are interested in discussing into the wee hours of the morning. We can keep going, but at least officially, I want to now connect. So far, we've just talked about this sort of wave equation. That's because it's a sort of familiar thing, and it's fun to see so much structure come out of such a simple and sort of familiar question. But now I want to start connecting this with cluster algebras. And I'm not going to say the word cluster algebra. I just said the word cluster algebra. I'm not going to assume that you really know anything about cluster algebras or tropicalization or anything like that, but just know that what we're talking about is intimately connected with these things. And actually what I'm doing here is kind of a poor man's way, a simple-minded person's way of asking a natural set of questions motivated from the pictures that we've been drawing, whose answers will end up being all the finite type cluster algebras associated with Dynkin diagrams and all the rest of it. Okay? And this is also going to connect with the general picture for building these isosahedra that Hugh Thomas and his friends talked about before. So I'll start off doing that, and and after we do that, we will move on to the second part of that. I'll try to do that part pretty quickly, just drawing a bunch of pictures. But after that, I want to move on to talking about just a more general question. In all of these stories, the Amplituhedra story and this story, in the end, we find some combinatorial or geometric object, but the connection to a physics comes via this canonical form that has logarithmic singularities on the on all the boundaries of the space. So this concept of positive geometries that we gave a more precise definition to with Thomas Lamb and John Tabai 2 years ago. So this is the key crucial idea that keeps coming up again and again. We have some space with boundaries of all codimension, and there's this unique differential form of logarithmic singularities that's tied to the space. A big question is, how do we find this form in general? And you can try to do it in many ways. You can try to triangulate the space into simpler pieces and add up the forms for the simpler pieces and so on. But it's really nice to have some canonical understanding or some canonical ways of doing it that don't involve triangulation somehow. Some presentation of what they are that's intrinsic and makes their a property of having logarithmic singularities as manifest as possible. For Amplituhedra, this is a big, giant open problem. We still don't know how to do that. But for polytopes, there are a number of ways of doing it. Not a huge number, but there's a number of ways of doing it. And some of them I'll review quickly, but there's a new way of doing it. And this new way of doing it actually doesn't directly build the canonical form, but starts off introducing a deformed version of the canonical form that's deformed by parameter alpha prime. Okay? Now, we call it alpha prime because that's what string theorists would call it in string theory, but it has nothing to do with string theory. Okay? It's just some totally generic thing. So we call these things stringy canonical forms. For any old polytope, you can, there's almost any old polytope, there's a way of building the canonical form that actually naturally has an alpha prime associated with it. And we will see that when at first that has a number of nice properties. Many of the things that people have seen in the amplitudes world in the past couple of years, the connection between scattering equations and the amplitude, the fact that you have mysteriously these formulas that show up that determine the critical points of string amplitudes as alpha prime goes to infinity, also give you, in another interpretation, the answer as alpha prime goes to 0, and so on. All of these things are totally general features of any old polytope. They have nothing to do specifically with string theory or anything, and we'll understand that as a general property of these stringy canonical forms, first of all. But secondly, we'll find that when we just apply that machinery, we take the stringy canonical form and we apply it to the isosahedron that we just talked about to build the form associated with the isosahedron, the alpha prime deformed notion will be string amplitude. Okay? No world sheet, no picture of correlation functions of vertex operators or anything like that, but just sort of directly going from this question in kinematic space. Now, answering the question in kinematic space actually will naturally lead us to talk about the string amplitude. So those are the two topics I want to talk about in an hour. Various people are laughing, but we'll see what we can do. So, okay, the first thing I want to do is actually talk about a kind of a practical question. We actually saw it in our examples that when we wrote down these Gauss's law equations, we found that if we wanted to solve them to see what the shape of the guy was, there was some kind of nice order in which to solve them. Right? We could solve them in some nice order and get a picture of what the space looks like. And that's actually completely obvious from this picture to begin with, if we now imagine time going in this direction rather than in that direction. Okay, now this is a two-dimensional picture. I could have from the very beginning said that time goes in this direction, and the reason I didn't is just because it looks a little more symmetrical when you do it like this. But anyway, let's now imagine time is running in this direction. It's a 1 plus 1 dimensional problem, so it's perfect symmetry between space and time. I'm going to imagine that time runs in this direction. And so now what is the problem that we are interested in? Now I want to imagine that you've given me initial Cauchy data here. So these are my x's that you've given here. And I just want to solve for what all the x's are inside, which I can clearly do. Okay? Now, how would you do it as a physicist? Well, you would just time evolve, right? You would just move this Cauchy surface along. And now how are we going to do it here? Well, it's obvious what I'm going to do here, right? So which one of the next of these points can I determine in the first step? If I've given all the x's here, this is 0. I can use, for example, the Gauss law. I know what these boundary values are. I know that's 0. So in this next step, I can determine this guy. Okay? In the next step, after I've determined this guy, I can determine that guy. Now I can determine that guy. Now I can determine, I can do a lot of things now. Okay? And you can see that I can just move this line through the picture, and that's just time evolution. Okay? And the advantage of doing that is that every step, I solve for the new variable directly, right? That's the point of evolving along Cauchy surfaces. I just solve for the next variable as it comes along. In every step, I encounter a new variable and I solve for it. Is that clear? Okay. All right, so we can do that. And we can also abstract out of this. We can say this a little more. We can say this a little more abstractly. So, for example, in this picture, to begin with, I have 4 guys in the middle. I'm not going to put these ones that are locked. They're sort of frozen to 0 at the top or the bottom. But associated with this picture, I'm going to draw a quiver. And the arrows are going to go, well, in the direction of the 45-degree lines. Okay, so in this case, all the arrows are going up because everything is going in one 45-degree direction. If it went the other way, I would draw an arrow the other way. And so what I've done is that I have some variables associated with all these nodes. I don't even have to call them x1, 3, x, whatever they are, x1, x2, x3, x4. But what I've done here in moving from there to there is now I'm going to have a new quiver with a new variable. So there's an x5 that I solved for here. But here I'm going to reverse the orientation of the arrow. The rest of them are still the same. So why have I done that? Because in this picture, now this new variable, here I'm going up, up, but the other way, there. Okay? So the direction of the arrows are just telling me about whether I'm 45 degrees in one direction or 45 degrees in the other. And what is this new x variable? This new x variable, I just solved for it. The new x variable is x5, is determined by the formula x5 plus x4 minus the guy that it talks to, which is attached to it, which is x3, is equal to some constant. And there's a constant that's actually attached to you see, it's interesting, the constant is attached to this square. Okay, so as I go, every time, so I make this move, and I write down this formula that solves for the new variable in terms of the old one. Okay? Now, the requirement that we are doing Cauchy evolution here is simply that the only nodes that I touch are only sinks. All the arrows are going into them. Okay? Well, you can see that in this picture, but I'm now going to say this more generally for any quiver. Okay? So take any old quiver, draw any quiver you like. Now we're going to have a sort of a new rule. We're going to have a rule for building new quivers out of old and new variables associated with the vertices out of old. So I'm going to orient the quiver in some way. I don't care. But it's going to look like a tree, say. So I'm going to have a bunch of variables associated with all the vertices. But now I'm going to allow a mutation. Of course, this is going to end up being just a subset of all the mutations that Lauren and Thomas were telling us about yesterday. Okay, so this is just a subset of the usual cluster mutations, except we've not heard about cluster algebras. We're just abstracting away the rule for Cauchy evolution that we saw in this picture and just trying to state for a general quiver. So we just mutate on any vertex, which is a sink, and I get a new variable associated with that vertex by solving the equation xb prime plus xb minus the sum of the x's associated with all the vertices connected to b by an edge is equal to some constant. And I get a new constant for every mutation as I go. Okay?
On any sink or source.
Only sinks.
Only sinks?
Only sinks. Only sinks. If I decide a source, this is giving me a sort of direction in which I'm walking. Okay, so if I'm deciding only going in this direction, if I did the other way, I'd be walking the other way. So here I'm foliating the space-time like this instead of like that. Okay? All right. Okay, so this is kind of a fun game. Okay, so take any old quiver, so we can do it with these linear quivers, and what's going to happen to me is, oh, sorry, and I'm going to say, of course, all my variables to begin with are all positive. S beginning are all positive, all greater than or equal to 0, and I'm going to demand that all these guys, that all the variables that I see along the way are also positive. So I want to say everyone is positive, all the x's are positive, but we satisfy these equations also with these sources positive. Okay, so it's pretty clear what you get, right? Like to begin with, before I do anything, let's say I just had, let's say I did this just in the simplest case. Let's say I did this for x1 and x2, and I write it like this. Then, in the first step, I'll get some x3 and x2, and I'd have x3 plus x1 minus x2 is equal to c. Right? So, what do I have at this point? I have that x1 and x2 are positive, but also that x3, which is c plus x2 minus x1, is positive. And so what I have in this first step is the region that satisfies all these inequalities looks like this. I cut something out here whose length is c. This is c plus x2 minus x1 is positive, so it tells me that x2 is bigger than c plus x1. Oops, sorry. X2 is bigger than c. Yeah. Sorry. Okay. And so then I just keep going. So I'm not done. But if I just keep going here, then what's going to happen is in the next step I'll get something like this. And then in one more step I'll get something like that, and now I've closed up the space. Okay? So I started with two variables. But the first step I walk, I get a third one. Then here I walk, I get a fourth one. And here I walk and I get a fifth one. And now two things have happened at this point. First of all, I finally got a closed shape. Okay? The closed shape is the icosahedron. So this is how I learned I have to stop when I see 5 variables. So one indication I need to stop is just that I closed up the space. In fact, a sort of more invariant way of saying when you have to stop is you can mutate any way you like in this way. But as you go, every new variable that you encounter, x new is going to be some sum written in terms of the original guys, with some written in terms of the initial guys with some coefficients. Call them some AI, plus something to do with these constants. Let's never mind the constants. Imagine for this purpose just setting these constants to 0. But if I think of this as a vector in this in the original space, these vectors are nothing other than the normals to this sort of polytope that I'm building as I go along. Okay, so I start from my original space, and then every new thing that I solve for is giving me some new vector as I go along. The rule is that I have to that I'm only allowed to do one of these mutations on sinks so long as the vector that I get is outside the cone of all the previous ones that I've seen already. And in fact, the way that it will end up going is that you'll sort of end up keep going until sort of at the very end you make in the last step you add a direction that then covers all of space. And so any new thing that you add would be inside the cone of the ones generated by the rest of them, and so you stop. So if I want to give a sort of a playful analog, this is time evolution, and this is some kind of notion of entropy, right? Some entropy has always got to increase as you go along. You're getting some new vector all the time. The new vector, this cone that you're making, has got to just keep getting bigger all the time, until it fills up the whole space, and then you've got to stop. Sometimes, if you do this, for example, if you do this if you do this for something like what will turn into A3, then you'll find as you go along near the end, there's some mutation you're allowed to do, which you could do, but which would not correspond to what we're used to seeing in what we're allowed to do in the cluster sense. And you also see that it's wrong because it violates this rule. Okay, so there are some mutations you're allowed to do purely because you have a sink, so you're allowed to do it, but you forbid yourself from doing it because it violates this rule. The kind of new vector that you see is needs to always be outside the cone of all the other ones that you've seen as you walk. Okay, so this gives you some interesting class of objects. You can ask, for which quivers is it true that this process stops, that you get something finite, and so on. Okay. I don't know if this is a theorem, but it is certainly true that if you do like random things, if you draw very simple quivers, what happens is it just never closes up. Okay? Just never ever closes up. So it's very, very special when the thing manages to close up. And the cases where it manages to close up, the quivers that you started with are orientations of Dinkin diagrams. Okay, so this is the connection. This is the poor man's way of starting with thinking about this wave equation. We have to take this step where we abstract away the rule for time evolution into the statement about mutating quivers only on sinks. But now we're time evolving through this space-time, and if we ask, for which quivers more abstractly does this give us a process that ends? It's the ones that are associated with orientations of Dinkin diagrams. And this is what you get.
Or do you mean mutation equivalent?
No.
Because
Literally
it's on
tree
listen
Dinkin
to
diagrams. And I'm starting with a tree. I have to start. Yeah.
Okay.
So I have to orient a Dinkin diagram. Yeah. Literally a Dinkin diagram. There's a little decoration that you could have on top of it. You might have factors in these relations. You might have factors in the relation, like when you have x plus x, maybe you should allow some integer, -2 times the sum of all the things coming in. Okay? And if you do that, that allows you to go from the simply laced Dinkin diagrams to the general Dinkin diagrams. Okay, but in this way, even allowing factors, this way of building polytopes by walking, or this abstraction away from what we saw in the wave equation picture in general, builds all of the finite type cluster polytopes. And this is so as I said, this is kind of saying backwards and interpreting in physicist-friendly language, assuming minimal knowledge of anything clustery, the construction of Hugh and its students. All right. Now, let me say something general that's kind of easy to discover. So let's go back to AN. So if I draw AN, then we saw that the polytopes that we get have the property that as you go to the boundaries, they factorize into lower polytopes of the same type. Okay? It's actually quite easy to see in general what kind of polytopes you ever see when you factorize. And what you see is simply what you get by deleting a node of the Dinkin diagram. Okay. So,
Can I just ask one more question? So what you're doing, is it correct that you're exactly computing cluster variables with respect to an initial cluster and tropicalizing them and writing down
Yes.
the plug? Okay. So that you could do for any
Yes.
quiver, not necessarily orientation of things.
That's right. But
then
what
if you want
I'm
the walk,
specifically doing with the walk, then it's orientating a tree Dinkin diagram. Indeed. Yes. Exactly. Yeah. So. Okay, so this is something cool. You want to see what are the kind of boundaries that you get from these polytopes. You draw your Dinkin diagram, you remove a node, and that's what you get. Okay, so that's what makes it obvious for AN that the boundary structure of AN factorizes into the product of lower ANs. Great. Okay, that's exactly what we needed for tree amplitudes. Right? That's okay. But now this also tells you what to expect for the other classical types that have an n associated with them. So for instance, I can take...
But it should work for any tree,
Okay.
right?
Sorry?
It should work for any tree.
It should work for any...
Tree.
Yeah, so it's all the... Yeah, all the... Yeah, it also works for them, but it's a little harder to... Well, I'll say something about it in a second. There's some... All right, so if we take this, so this is for B or C type. I don't care about the orientation of that arrow here. So if this polytope is, I don't know, let's call it P, what does it look like when I remove a node? When I remove a node here, so let me call this B, let's say. When I remove a node, the boundary of this B-type polytope is going to be another B-type polytope times an A-type polytope. An A on one side and a B. Okay. What about Dn? So this is a little more cool, because what's the boundary of D? Now this has two kinds of pieces. One piece is when I remove something like that. And so one kind of boundary looks like a D cross an A. So this part looks like a D and the rest looks like an A. But there's a more fun part where you delete one of these. That just looks like a single other A. So there are two kinds of boundaries that we get from this polytope. Right? So if I summarize, the kinds of polytopes that we get from this construction that are associated with this generalization of time evolution in the spacetime, abstracted away to this to this walk associated with the quivers. For type A, I get boundary of A is A times A. For type B and C, let's say B, I get boundary of B is A times B times A. And for type D, I get a boundary of D is D times A plus another A.
What if
Yeah.
you delete the trivalent?
Yeah, if you delete the trivalent one, you might freak out a little bit, but this is in fact nothing other than D2.
Oh, okay.
Okay, so fortunately, yes, it looks a little funny, but this is a special case of D times A, because this is A1 cross A1, which is the same as D2. We'll come. E6 is more interesting, so we'll come to it in a second. Okay, now since I'm just drawing pictures, I can at least say what these things correspond to. So these things all correspond to physics. These things correspond to tree amplitudes. Phi cubed, phi adjoint tree amplitudes. Now, what does this look like? This is exactly what you get if you had amplitudes involving the emission of some uncolored dilettante, or just summing all the tadpole diagrams, right? Because if you factorize this, what are you going to get? You're going to get if you factorize this guy, you're going to get a tree amplitude on one side and something that involves an emission of something on the other side. And so what these things are going to factorize into are trees on one side and lower objects of the same form on the other side. And so that's why these correspond to the sum of one-loop diagrams where you include tadpole emission. And finally, this is, of course, the most fun one, because this is exactly the fact that one-loop amplitudes can factorize into one loop and tree. But we can also have the lower tree amplitude where we take the internal propagator, some internal propagator, and we just cut it open, where we put it on shell. That's to physicists, our famous friend, the forward limit. So the rest of this down here is a tree, but when I take some internal line and I put it on shell, I get two more particles and a tree amplitude. So that's the kind of factorization you have to have at one loop. You have to have something that factorizes into itself times tree, as well as just a tree, but with two more particles. Okay? And that is on the nose what you get from these pictures. So just the fact that these polytopes abstractly have this factorization property also tells you that it's guaranteed when you associate a canonical form with them, pull back to the subspace, blah, 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 all the rest of it exactly as we did before. Whoa, sorry about that. You are going to get, just 1 second. Let me do something real quick. 1 second. Hold on. Okay, sorry. Just throw one more. I don't want you to slip. Okay. So that's all I wanted to say about that. So this connection of the connection, and in all of these cases, again, you get a projective form, there's this hidden symmetry, there are new triangulations, blah, 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 new recursion relations, all of it works. But this is the sort of conceptually important point, is that we get structures that have a good abstract reason for giving us exactly the kind of factorization properties that we associate with amplitude, at least through to one loop. Okay. So now let me switch gears to the last topic. Yeah. So in this way, there are these geometries in kinematic space now enriched with loop variables up to one loop. And there's this question in the kinematic space that involves this time evolution walking with this quiver. And the answer to that question gives us amplitudes through the one loop.
So
Okay.
does
Yeah.
this one loop correspond to genus one surface and you kind of kill one, or it's not?
Kind of. I mean, the connection with DN is just as you'd expect. It's the cluster algebra with one puncture on the inside, and that one puncture on the inside is exactly. I mean, that's why you'd expect. If I just told you what could DN be about, you would say an endpoint on the outside, I have a puncture on the inside, and so these triangulations begin. The most obvious ones just look like a one loop diagram. This is the graph dual to a one loop diagram. Okay, so if you know about cluster algebras, these are the most obvious things you would start to do, right? You would say trees are just the usual triangulation of the polygon. I put a puncture on the inside, that's one loop. So what's two loops? Put two punctures on the inside, and that's great. That's a wonderful place to begin. The difficulty is, as I alluded to before, and as you know better than I do, is that the cluster structure now associated with two punctures on the inside has an infinity in it. Okay? Generically, is the infinite. And the infinity, what is the infinity? The infinity, in the language of sort of pictures that Lauren was drawing yesterday, is that we don't, we only care about the fact that there is something going from this boundary point to this guy in the middle. That's one of our loop variables. We don't care about how often this thing is winding around before it goes from one thing to another. Okay? That's not something that the scattering amplitude knows or cares about, but the cluster structure knows or cares a lot about it. And so that's the zeroth order problem that we've been struggling with for a while, is to figure out how to sort of mod out by this thing that's naturally there in the cluster structure, importantly there in the cluster structure to keep track of the combinatorics of mutations, but which we do not want to have in the amplitude. Okay?
Does it mean that you quotient by the mapping class group?
We would love to know what those words mean precisely. Yes, what we want to do is quotient by the mapping class group. But what that means, what the words quotient by the mapping class group means at the level of this ersatz polytope that we're trying to build is a thing that we don't have the answer to. Okay, so, and I think this is an interesting question purely to a cluster algebraist, right? For finite type, we know there are these beautiful polytopes that capture the combinatorics. In infinite type, what kind of infinite polytope captures the combinatorics? Is there a polytope that captures the combinatorics? If so, how do you think about it? If not, is there a way of quotienting it? So there's some kind of object, maybe not a polytope, maybe some, I don't know, something, but something which does the analog for the infinite type cases. So that's the sort of missing thing in this story as far as the connection with physics is concerned. For the amplituhedron, we have the story to all loop order. For this, ironically, for this dumb bi-adjoint phi cube theory, at the moment we only have the story through to one loop, and it's because starting at two loops we have to encounter on the cluster side this infinite issue to deal with.
And does it follow from the fact that your form is just invariant under this mapping class group action? No?
It should be, yes, because the form doesn't even know about it. That's what I'm saying. The form doesn't even know. The form just knows about the beginning and end point.
Expression for the
right.
form is literally the same, not like.
Yeah, that's right.
Okay.
Yeah. So in fact, yeah. If I had longer, I'd say a little more about this, but we don't have a clear picture yet. So I think this is a very beautiful open problem to try to figure out what does these words quotient by the winding around. What does the word quotient by mapping class group mean at the level of the combinatorics, at the level of some ersatz polytope that would capture the combinatorics and so on. If there's an answer to that question, then we would know the answer for phi cube theory to all loop order. I think that's the only missing ingredient. Okay, so let me now move to the last topic. I'll have to be, unfortunately, brief. Last topic is stringy canonical forms. And this is work with Thomas Lamb and Song Hay. And again, the motivation here is how do we find these canonical forms? How do we find this canonical form associated with some polytope? So, let's say I have some polytope. Let me just go back, very general question. I have some polytope P, there's some coordinates Y in the space. How do I find the form on Y space that has logarithmic singularities on the boundary of the polytope? Okay, so how do I determine this form? And as I said, for polytopes, we have a few nice answers to this question already. One of them is that, so one answer is that this canonical form so if I think of y as just living in some projective space, polytope living in the projective space, the canonical form for y and p is actually, there's this universal, you have an n-dimensional projective space, there's this universal measure on the projective space, and it multiplies the volume of the dual of the polytope, where now y is thought of as the hyperplane of infinity. Okay, so this is one nice invariant formula. Okay, so the canonical form of a polytope is the volume of the dual of the polytope. We would love to have the analog of this formula for the amplituhedron, and that's this mythical object, which may or may not exist. That, if it does, would be the dual amplituhedron. That would give the analog of this for the amplituhedron. I think maybe precisely 3 people in this room, 4 people in this room. I won't get in trouble again. Last time I said only 2 people. 4 people in this room care about this object, okay? But all 4 of us think that it exists. So, all right. Okay. There's another formula that I actually talk about in my colloquium. So, second formula I won't talk about now. It will play a role in my colloquium. There's a third thing which is interesting, and is going to be, and we're going, and I'll just mention. And it's the following. So let's say you have one polytope. It's to be more generally true for more general positive geometries. But let's just say you have one polytope P1, and you find a mapping of that polytope to some other polytope. They don't have to even have the same shape. P2, we'll give some interesting examples in a second. So in fact, the sort of interesting case is when this one is simple, and you find a way of mapping it into something complicated. And so let's say you find a map from this space, little x, to this space y. So you have some map that maps every point in here to a point in there. Then if we push forward, so if on this space we have the canonical form on P1, the canonical form on P1 in X pushes forward under this map to the canonical form in Y space for P2. Okay. What that means is that if I just literally sum the canonical form in X over all the pre-images of any point here Y, so a given point Y here can have many pre-images back in X space. So I just sum over all of the xi's for which Y of xi is equal to some, or let's call this map phi, for which phi of xi equals Y, then this gives me the canonical form on P2 and Y. So there's a very simple and general reason for that, but I won't explain it here. So that means that if you have a way to map from a simple space into a complicated space, then all you have to do is you might have to solve some algebraic equations, let's say, to determine all the pre-images here. But if you sum over all the roots of that equation, you evaluate the form on all the solution, all the roots of that equation, then you'll get the canonical form on the space that you want. Now, here's a very nice application of this. Application is what you can think of as the Newton polytope map. So let me just say very practically what it is. So let's say I have a polygon, and I have my vertices of the polygon Z1, Z2 up to some Zn. Again, normally I know that I can write any point on the inside of the polygon as some weighted sum of these guys, with these coefficients being positive, but of course this is a many to one map. So what I'd like to do is find some way to parameterize all these C's in terms of, in this case, just two variables, such that the map from the space where those variables are positive to y space is 1 to 1. And the way to do it is the following. You just pick an integer representative of the polytope. So let's say you want it to map into a pentagon. You would pick some integer representative of a pentagon, or in general, something which is the polytope of the same shape. So let's say I wanted to get this pentagon with Z1, Z2, and so on. Z5. So I would draw this and here's my map. I would say that y is equal to C1, Z1, so C1 is going to just be 1. C2 is going to be some variable x1 to the 1, C2. C3, so I labeled these the same way, 1, 2, 3, 4, 5. C3 is going to be x1 squared x2 times Z3. C4 will be x1, x2 squared Z4, and C5 will be x2, Z5. Okay? And now the claim is that so long as just x1, x2 go from 0 to infinity, that this map, 1-to-1 maps, it sort of foliates the entire inside of this pentagon in terms of these variables that are just positive. And so x1 and x2 just are positive, so I'm mapping this upper quadrant for x1 and x2 into the inside of this polygon. All right, there's lots of ways of, let me just give some intuition for why this is true. The first thing is it's actually very easy to check. So in general, let's just say what we're saying in general. In general, we would say that we would write y is equal to the sum over all the vertices of some x1 to the v1a, x2 to the v2a, so on, some xn to the vna, za, and I'll abbreviate this as the sum over all the vertices as x to the va. So it's clear what I mean by this. It's just the product of all the powers of the x's, and the v's are just some integers. Okay, za. But really what makes the whole thing go is that if you look at the Jacobian of this map, you look at det dyi by dxj, and there's as many i's as j's. There's a very simple formula for this, which is proportional to the sum over all the minors of these v vectors times the corresponding minors of the external data. That's an extremely simple computation. And so if this integer polytope has exactly the same shape as the polytope you're trying to map into, this is the sum, this is a square of something. So this is positive. So this map can't have any sort of fixed points inside. Okay, so in the interior, it's generically 1-to-1. And then life is easy after that, because then you just have to figure out what's going on near the boundaries. But it's pretty obvious. If you head off in a generic direction to infinity, if you just head off in a generic direction, only one of these exponent vectors is going to dominate over all the others. And you'll actually just end up at one of the vertices of the polytope. Okay, so if you head off in x direction in a random direction, you'll end up in the basin of attraction of one of the vertices. So you're not going some random place. If you head off in a random direction, you'll end up in one of the vertices of the polytope, and if you go anywhere else, you'll end up on some facets of the polytope. So everywhere as you go, in the interior it's one-to-one, and on the boundaries you're just going to hit the boundaries of the polytope. That's at least intuitively why it's true. And so therefore, this is an example of exactly what we want. It is a map from the interior of a polytope. It's from the interior of a simplex, inside of a triangle, this projective simplex, into this polygon, or into the polytope in general. Okay, but so if I say super explicitly and not projectively, I mean really super duper explicitly, here's the statement. I really want sort of like some vectors in some affine space, and I will just define them as the sum of, maybe with some coefficients even in front, it doesn't matter, gamma A x to the VA times ZA, this is the coordinates of my polytope, and so these are my positive weights, so I'll divide by them. So divided by the sum over A, gamma A x to the VA. So these are my positive weights, the CA, and here I'm just summing over all the CA. Right, so this is the weighted sum of all the points, and the claim is that if the VAs have the same shape as the ZAs, then this is a one-to-one map, and it maps the X space into the polytope. All right? And furthermore, if I take the form dx1 over x1, therefore dxn over xn, that this pushes forward into the canonical form for the polytope. What this means, again, concretely, is that I have to just sum over all the solutions of all the solutions of these equations for x, which set x equal to y. Okay, so all the pre-images of y under this map. So all the solutions of y of x equals some capital Y. It just means the canonical form on y. Okay, so that's one idea. Okay, so that gives you a way, if you have any polytope, if you can give an integer representative of the polytope, then you're up and running. Okay, you have some way of building this canonical form as a push forward. That's almost all the polytopes we care about. Not every polytope can be realized with integer coefficients. I learned it's kind of a bizarre thing. There are crazy polytopes that have to have irrational coefficients in their vertices, but all the ones that we care about in physics don't look like that. Okay. So now there's another idea. So that's a review of some of the existing ideas. Now there's another idea, kind of related, loosely related. Another idea is the following. Let's say we have a canonical form, even something simple like the canonical form of a simplex. So these x's are just positive variables. Why don't I just integrate these canonical forms over the places that they're canonical? Why don't I do that? I have a form, I have a region. Why don't I just integrate them? Okay, well, we start doing it, and we see, of course, why I don't integrate them. This is a completely stupid thing to do because they're designed to have logarithmic singularities on the very space we're trying to integrate them over. So if I do this, I'm going to get nonsense. Right? But let's press on and just try to regulate these integrals in some way. So for instance, this is going to have some difficulties as all the x's go to 0. So we can say this a little more elegantly and generally, but I want to do it a little more intuitively. So let me regulate by putting some factors like this.
What are capital
Okay.
X size?
Sorry?
What?
These xi's are now just some numbers that I'm going to demand to be are positive. Okay? So if I demand these numbers are positive, and alpha prime is some parameter. Okay? Alpha prime is some small parameter. Okay, so clearly there's some divergence here, which is now being regulated by something that will look like 1 over all the x's. Okay, so the whole thing is going to go like 1 over alpha prime to the n. So let me normalize the whole thing by putting an alpha prime to the n in front of the whole thing. Okay, so now at least one piece of the behavior of this thing is alpha prime goes to 0. We've regulated the behavior near x equals 0. Okay, but I'm not done. I also have trouble at infinity. So let me try to solve the trouble at infinity just by putting a giant polynomial of x's. Just a polynomial of x's, let's say with all positive coefficients, to a negative power. Okay? So this gives me some function which has been regulated now. It depends on all these capital X's and it depends on this C. So, for example, if I just do this in the dumbest case of just one variable, I would put x to the alpha prime capital X. And then to regulate things, I could put the polynomial 1 plus x to the minus alpha prime C. Okay, and if I now switch variables from x to something that goes from 1 to t, we can recognize this as the integral dt over t1 minus t, the integral we've seen many times in this workshop. The beta integral, or the Veneziano amplitude, t to the alpha prime x, 1 minus t to the alpha prime x minus c. So this is the beta function. And now notice something. Now we learned that we had a chance for this integral to be convergent, right? We've given it a chance to be made convergent because we've regulated x equals 0, we potentially regulated x goes to infinity, but clearly I have to be careful. I can't make these x's enormous, for example, because that might overwhelm whatever I get from p of x. So the x's have to be somewhere. They have to be somewhere for this integral to be convergent. And we see that very clearly here, right? In order for this integral to be convergent, I need to have that, oh sorry, this is c minus x. I need to have both that x is positive and that c minus x is positive. So x itself has got to lie between 0 and c. So x has got to lie somewhere in there. Okay? Okay, so in this way we've recovered our friend the open string amplitude. I'll just say that there's an analog of everything here for the closed strings, but I don't have time to talk about it. Okay, so we can do essentially exactly the same story. You do some analog of not quite a mod squared, but you can take this thing with a p and a p prime, and these powers have to differ by integers in general. You can complex conjugate and multiply it by something else where the powers can differ by integers, and the whole object is well defined, and there's an analog of the closed string integral that we could talk about as well. Okay, but let me just talk about the open string. All right, so let me just make some claims about this object. Once we see this extremely simple example, I hope the claim will be plausible. So the claim is, when does this thing converge? In general, the claim is that the integral converges exactly when those x variables, the whole vector of x's, lie inside C times a certain polytope, and the polytope is the Newton polytope of the polynomial P. The Newton polytope of a polynomial is just what you get by taking all the exponent vectors in the polytope and just thinking about them as integer vectors in some lattice. You just take all the exponent vectors and take the convex hull of all the exponent vectors, you get some polytope. And so the claim is, so in this case, what was the Newton polytope? The Newton polytope would have just been the integral 0 to 1. Okay? The Newton polytope of this guy would just have been the point 0, 0 and 1, 0, so just be the integral 0 to 1. And so that's what we see. X has got to lie inside C times that Newton polytope in order for the integral to be convergent. Okay? So this is true more generally. And furthermore, if I called that integral, I should have called it I alpha prime, that depends on these x's. If I further wedge that thing, dx1 through dxn, that's just for fun, then it's also true that it's going to have singularities, poles, when the x's approach the boundaries of this Newton polytope, obviously. And so it's very reasonable that what this guy is actually the canonical form of the polytope, at least in the limit as alpha prime goes to 0. And the limit as alpha prime goes to 0 of this thing turns into the canonical form in x space of this polytope C times P. Okay, so that's yet another definition of the canonical form of a polytope. Any polytope that I can realize as the Newton polynomial of some polynomial, any polytope that can be given integer vertices if I like, for any such polytope, I can realize its canonical form as alpha prime goes to 0 by actually naturally building an alpha prime deformed version of the same thing. In fact, it's a natural object already at non-zero alpha prime, but as I send alpha prime to 0, it turns into the usual canonical form. Okay, any questions about this? So I'm going to say a few things pretty rapidly. Now this object has nice properties even when alpha prime is not equal to 0, but let me focus on the behavior. Let me just focus on the behavior as alpha prime goes to 0. So one thing we've said already, this turns into the canonical form. But let's look at something else. Let's look at what happens as alpha prime goes to infinity. Well, as alpha prime goes to infinity, we have this integral dx1 over x1, blah, blah, blah. Then we have x to the alpha prime x, p of x to the minus alpha prime c. And so the saddle point equations of this integral as alpha prime goes to infinity, you can think of as sort of generalized scattering equations. Well, just the saddle points. We've been saying nothing about scattering amplitudes or anything here. This is just about polytopes. But given how ubiquitous they've been in physics, so what are these equations? Well, in this case, they were just trivially just the saddle point of this thing. I'll just write it down. They're just that these capital Xi over the little xi's minus 1 over p dp by dxi is equal to 0. Right, that's just the saddle point of the integral. Okay. Now, these equations have a very pretty interpretation. Let's just regroup. So let's say that the p of x is this polynomial. So I'll write it as sum of gamma a x to the ba. Again, this is a polynomial in many variables, but I'm writing it in terms of this order. This is x1 to the ba1, x2 to the ba2, and so on. Okay? So what is dp by dxi times xi? This is the sum over A, sum over all the vertices of the Newton polytope, the sum over A of BA, gamma A, BA, I, x to the BA. Right like that. This is an equation for each I separately. Okay, so what is this telling me? If I think of this as an equation for all the x's together, this is telling me that x is equal to the sum, just multiplying by xi, is equal to the sum of gamma a, ba, x to the ba, divided by the sum over a, gamma a, x to the ba, which was just the p itself, right? That's exactly the Newton polytope map. The Newton polytope map. And therefore, in complete generality, if I push forward this d log form, dx1 over x1, dxn to xn, on the support of these scattering equations, I'm going to get the canonical form for the polytope. Done. So this is a sort of a one-line conceptual explanation for why there is this relationship between the alpha prime goes to 0 and the alpha prime goes to infinity limit of the sort of same object. Okay, so on the one hand, we have these integrals that as alpha prime goes to 0 give us the canonical form for the polytope. On the other hand, the stationary points that we get give us a mapping, which is the Newton polytope map, into the same polytope. And so if we push forward on that map, we again get the canonical form for the same polytope. Okay? Okay. Now, this is not what we normally see in physics. We don't see something quite so simple. But let's actually immediately generalize this. There's a trivial generalization.
We should at
Yeah.
least give people a
Yeah,
quick
yeah.
break between.
Oh, yeah, sorry. So let me just say this quickly. Sorry. That's just 3 minutes, and then I want to get to at least one punchline. But there's one semi-punchline. But let's now talk about a slightly more general integral, where dx1 over x1, blah, blah, dxn over xn, all of these guys. And let's say I have a bunch of polynomials here. P1 to the negative alpha prime C1 up to P from J to the negative alpha prime Cj. Then what am I going to get? So if I take this thing and I wedge what the dx is and I send alpha prime to the unknown front, what I'm going to get is the canonical form in X space. Now just for the Minkowski sum, C1, P1, for the polytope that's a Minkowski sum of all of these polytopes. Okay, there's a very simple way of seeing that. If you just imagine for a moment that these C's were rational, then you can actually just think of this as one gigantic polynomial to a very fractional power, and then we apply the old story. So it's nothing has changed, and so what we get is the Minkowski sum. It's a canonical form for the Minkowski sum of these pieces. So what this tells you is that this formalism is especially useful when you have polytopes that are naturally handed to you as a Minkowski sum. If they're naturally handed to you as a Minkowski sum and you want to get the canonical form, just do this. Right? So finally, let's apply this to the simplest case. Let's apply this to Isosahedra. Okay, so for example, let's take that example that we did for 5 points, where we saw that we could make the isosahedron as the sum of these, Minkowski sum of these 3 pieces. And so what are the associated Newton polynomials? It's like 1 plus x, 1 plus y, and 1 plus x plus xy. So what is the integral that we're talking about? It's the integral 0 to infinity dx over x, dy over y, x to the a, y to the b, alpha prime a, alpha prime b, 1 plus x to the alpha prime c, 1 plus y to the minus alpha prime c, minus alpha prime b, 1 plus x plus xy to the minus alpha prime e. Okay? And you may not immediately recognize it, but this is literally the integrals that Sebastian was talking about. These are the most canonical string amplitudes. Okay? So this is the same as the integral d2 times dz1 through z5 over z1 minus z2, blah blah, z5 minus z1 mod SL2, and then the product over all I and j, zi minus zj, these called the Nielsen factors, the alpha prime Sij. Okay? They're literally the same, just with an identification of these exponents with the variables that occur there. So, in other words, what we get from here, we know that what we get from here, if we're trying to build the canonical form for the isosahedron in this alpha prime deformed way, because the isosahedron is handed to us in this natural way as a Minkowski sum, the object we're getting, of course, gives us the canonical form for the isosahedron as alpha prime goes to 0, but at finite alpha prime, it gives us the string amplitude. from literally the construction, not a random construction of the association, but the construction of the association that we talked about, associated with the space-time picture and the quiver and the walk and the cluster structure. All right, so that's now our journey from kinematic space to now asking some way of realizing these, some way of actually determining these canonical forms. There's a natural way of associating them with an alpha prime, and that actually leads us to string amplitudes. And of course, the miracle of these string amplitudes is that they will factorize perfectly on all the poles, even when alpha prime is not equal to 0. The final thing I'll say is that you can, since the story is so general, you can actually generalize this to all of the finite type cluster algebras. Okay, so there's an analog of string amplitudes associated with all the finite type cluster algebras. They have no worldsheet interpretation. We don't know how to think about them in any standard way. But they have the property, they make sense at finite alpha prime, and at finite alpha prime, they inherit exactly the factorization properties that we saw before. So for example, at finite alpha prime, for the dn case, there's an object which will factorize on the poles into the product of a d and an a, and all exactly the same properties that we saw before. They have all the qualitative properties of string amplitudes. They're exponentially soft at high energies. They have the analog of Reggie behavior. They have the analog of channel duality. All of those things are very, very generic features that are there for all of these examples. We don't know, the burning question is, so we think they're fascinating objects, they're interesting to try to understand. We don't know how they're related to ordinary string amplitudes. If they're related to ordinary string amplitudes, it seems utterly bizarre that such an object should exist with all the same kind of qualitative properties of string amplitudes and not be the string amplitude in some sense. And we also know that in the alpha prime goes to 0 limit, they agree with one loop field theory amplitudes. So they're not some totally garbage thing. We talk about dn, there's something that reduces to a one loop field theory amplitude in the appropriate limit. So it's a very interesting question to try to understand how these things, if they're related to actual string amplitudes. And of course, we can talk about them in all the other types, G2, E6. These are sort of weird, interesting objects, and it would be really, really wonderful if they had some role to play in physics. It's not obvious if they do, but they're certainly mathematically interesting to think about. Okay, I think that's it. Thanks.
I think we should thank Nima for.
No, there's no coffee yet. I'm still giving a quote.
Well, yes, but it's officially the end of just the workshop, and then you're closing separate.
Oh,
so I
okay.
think we can-
All right. I didn't know that.
Yeah.
Focus first now, right?